Hello and welcome to another Mr. Mike Maths video. This time we're attempting question 6 from the October 2021 Edexcel Decision Maths paper. We're told that in figure 4, the weights on the arcs represent distances, and we're asked to use Dijkstra's algorithm to find the shortest path from A to H and state the length of the shortest path from A to H. So we're going to start at vertex A. So we've labelled A first, and it has a final value of 0. So now I'm going to update the working values of all the vertices connected via an edge to A. So B is going to receive the working value of 32, D 75, F 95, and C 16. We're now going to visit the next vertex with the smallest working value that hasn't yet been visited, and that's going to be C. C has been visited second with final value 16. And we're now going to update all the working values of vertices that haven't yet been visited but are attached to C. So we're going to get 16 plus 50 is 66. And I have a feeling that D is going to be visited a few times, so I'm going to just make some more space. So we've got 66. 16 plus 70 is 86 for F. For G, we're going to get 121. And for H, we're going to get the value 129. So I'm now going to visit a vertex with the smallest working value that hasn't yet been visited, and that's going to be B. We're visiting B third with final value 32. I'm now going to update the working values of vertices connected to B that haven't yet received a final value. D is going to receive a working value of 65 because 32 plus 33 is 65, and 32 plus 15 is 47 for E. I'm now going to visit the vertex with the smallest working value that hasn't yet been visited. That's going to be E. We're visiting E fourth with final value 47. And I'm going to update the working values connected to E. 47 plus 17 gives 64 for D. And 47 plus 30 gives 77 for F. I'm now going to visit D. D has the smallest working value out of D, F, G, and H. So I'm visiting D fifth with final value 64. And I'm going to update the working values attached to D. There's only one, and that's 64 plus 50 is 114. I'm now going to visit F, because F has the smallest working value out of F, G, and H. So I'm visiting F sixth with final value 77. I'm going to update the working values to the vertices attached to F. 77 plus 25 is 102. 77 plus 41 is going to be 118. I'm now going to visit G. G is being visited 7th with final value 102. So I've got to update the working values of all the vertices that haven't yet been visited that are connected to G. That's going to be H with a working value of 112. So finally I'm going to visit H last, and it has a final value of 112. So I know the length of the shortest path from A to H is going to be 112. And to find the shortest path from A to H, I've got to backtrack. I've got to take this final value of 112. If I go down an edge and take the weight of that edge off, the final value at the other side of the edge is the final value subtract the weight of the edge. I'm going to have visited that node first before visiting H. So I'm going to go H. If I backtrack to G, that also works. I'm going to start at H at the end. I'm going to backtrack to G. 102 subtract 25 is 77. So I'm going to get F. 77 subtract 30 is 47, so I'm going to have gone to E before F. 47 subtract 15 is 32, so I'm going to get a B. and 32 subtract 32 is 0, so I'm going to get A. So the shortest path is A, B, E, F, G, H. So, how are the marks awarded for this? Well, there's a method mark for a larger value being replaced by a smaller value in at least two of the working boxes at either D, F, G, or H. So any of the boxes where working values have decreased, as long as there's been a larger value being replaced by a smaller value in at least two boxes, that is going to be a method mark. You then get an accuracy mark, and I'm going to do this in a different colour. An accuracy mark for getting all the values in A, B, C, and E correct. So A, B, C, and E. Then another accuracy mark for getting all the values in D and F correct. So D and F are the next accuracy mark. Then finally, an accuracy mark for getting G and H correct. And this accuracy mark is a follow-through mark, so it could have had one mistake followed through to get this mark. Finally, there's an accuracy mark for getting the correct shortest path, and an accuracy mark which is a follow-through for getting the correct shortest distance. Okay, question B. One application of Dijkstra's algorithm has order n squared, where n is the number of nodes in the network. And a computer produces a table of shortest distances between any two different nodes by repeatedly applying Dijkstra's algorithm from each node of the network. It takes the computer 0.082 seconds to produce a table of shortest distances for a network of 10 nodes. Calculate approximately how long it will take for a computer to produce a table of shortest distances for a network of 200 nodes. You must give a reason for your answer. So Dijkstra's algorithm has an order has order n squared, but this is only from one node. So if we apply Dijkstra's algorithm multiple times to n nodes, so Dijkstra's algorithm n times has an order of n cubed. And this is from n nodes. And this is a scenario in the question. We're doing Dijkstra's algorithm multiple times, repeatedly applying Dijkstra's algorithm for each node in the network to produce a table of shortest distances. So this scenario has an order of n cubed. So now we can calculate the time. The time taken is going to be the 0.082 seconds from the scenario with 10 nodes, or n is equal to 10. We've only got to multiply this by a scale factor. So if we're increasing the size of the problem from 10 to 200, the scale factor is 200 over 10. But this is only the scale factor for n. And we've got an order of n cubed, so we've got to cube this 200 over 10. So our time is going to become 0.082 times 200 over 10 cubed, which is equal to 656 seconds. So what marks would you have got for this? You would have got a method mark for saying that the order of this scenario is n cubed. You got, not a method mark, an independent accuracy mark. You've got a method mark for multiplying the all time by 200 over 10 cubed. and an accuracy mark for carrying out that calculation correctly. So finally C, explain why your answer to part B can only be an approximation. And it's to do with what we mean by an order of n cubed. An order of n cubed does not mean that the order is proportional to n cubed. So by that we mean some multiple of n cubed. What it actually means is that the dominant term is n cubed. Or the dominant term has an order of n cubed. So dominant term is n cubed. So we could have a scenario like kn cubed plus an squared plus bn to the power of 3 halves plus the square root of n. And as n gets really big, the n cubed dominates this term. So all the other terms become negligible. But whilst n remains small, these other terms can impact the size of the problem quite a lot. So this is only an approximation. If we had 20,000 for n, it'd be a really good approximation, but because we've only got 200, these other terms can still affect it, especially if their coefficients are large. So we've reached the end of this question. This part of the question will have been an independent accuracy mark. So until next time, thank you and goodbye.